So let's start with a thought experiment. Here's a picture. This has happened to be a scene from 2001. And so what we want to do is to represent the information in that picture using a voltage. So imagine, this is the way TV worked for many years, not anymore, but in the old days. What we're going to do is to take a horizontal scan across the picture, across the TV picture, in this case, or just an image, and it's a black and white image. And what we'll do is we'll represent black as 0 volts. So here's my voltage scale here, and at this end of the scale will represent basically no luminosity at all, and at the higher end of the scale we'll get white, and then as I scan across I would expect to see a continuous waveform like so, where these pixels up here are white, and this part of the image, as I scan across, this part of the image is, so this is basically the distance. And this is the voltage. Okay, so that's a pretty simple representation. And the percentage of the voltage between 0 and 1, we'll just call this 0 volts and 1 volts for the sake of argument, tells us how bright, where we are in the grayscale. So the first question I want to ask you, and this is food for some thought, is how much information can I store using this encoding technique? Using encoding information this way, how much information can I store about the image? Forget going from line to line to line on the raster. Let's think about a single raster line. Yeah, in the back.
You can store information as fine-grained as you can represent it, as you can present it on the receiving end.
Right. So what you've observed is that I'm using a continuous value, which is a voltage, to basically store information about a continuous value, which is the luminosity of the image at that point. And in some ways, you could think of that as almost being an infinite amount of information. And you can sort of say, well, here you are with your mathematical hat on, and you're all saying, wow, that's great, that works well. Now the downside of that is, in fact, that we are limited by the real world, which will sort of get in the way, as we'll see. So let's continue our thought experiment. Let's design 2 processing elements, one of which is a copy element that takes in the voltage encoded luminosity, so a voltage of between 0 and 1 volts, and simply reproduces that voltage on its output. And then a second building block is the inverter, which will invert the voltage. If I put in pure white, I get out pure black, so forth and so on. So those are our 2 basic building blocks. So first of all, you might ask, why are we bothering with building blocks? What good are building blocks? Well, what we want to do is to introduce sort of a level of abstraction. If we have an engineer in the back who's busy wiring together, cameras and projectors and screens, they don't really want to have to whip out Maxwell's equations each time they have to figure out what's going on. We want to sort of give them some level, building blocks that they can piece together to make an engineering system without having them. They want to understand the behavior of the building blocks without understanding the implementation. So that's a real key to successful engineering of complex systems, is to introduce these levels of abstraction. And in this case, I have a very simple system that consists of these 2 blocks I can wire together to do, I wouldn't say interesting things, but at least the start of a video processing pipeline. And we expect to be able to wire these together sort of in arbitrary ways. And we should be able to reason using our abstraction. We should be able to reason about what the output should be and hope to be correct. In other words, we want to be able to compose a system out of these abstract, higher levels of abstraction building blocks and still expect everything to work well, even in the real world. So not in the mathematical world, but when we actually bolt it together, the right thing happens. Okay, so composition is a reason, we're trying to put, we're building, as it will turn out, 5 or 6 layers of building blocks throughout this course. And we hope to be able to, that our abstraction is good enough that we'll be able to use them without knowing what's inside each building block. So let's build a system. We have some copies and some inverts all wired together. I think this is all set up so that I'm expecting exactly a copy of the picture to come out. And, mathematically, that would, you could just sit down and sort of figure out what the value, for a value v on the input, you can figure out mathematically what you expect the value of v on the output to be. And in fact, it should be the same value. But in practice, it's fuzzy. What went wrong? Okay, what was there about things that caused the system that we built to not behave quite as we hoped as engineers? And you can sort of say, well, engineering sucks. I want to be a mathematician where I don't have to worry about these problems. But to me, the charm of engineering is exactly in wrestling with figuring out what went wrong and then coming up with a way to get the right thing out, even though the world is sort of playing Maxwell's demon with you and wondering if it can screw you up somehow. Okay, so the first thing you can notice is that maybe our operators aren't quite perfect. For example, the copy operator may not, for v volts in, produce exactly v volts out because of manufacturing variations or the fact that it's a little warm in the room or the fact that the power supply is a little off. I may not get v out. I may get v plus or minus epsilon out. And you can sort of say, well, epsilon doesn't seem very big. Epsilons are never very big. Epsilon is destined to spend the rest of its life being small. And you can say, okay, so why do I care? Well, the reason that we care is that in this analog world, in this world where every possible voltage has an actual interpretation, interpretation is a luminosity, okay, why we care is in fact that errors accumulate. In other words, if I'm off by a little bit on the first copy operator, the rest of the system doesn't know that the first copy operator was off by a little bit. It just assumes the picture was a little different. And so this accumulation of errors in these analog systems, these continuous representation systems, okay, is a real problem for us. So that probably means that in some sense, and the reason it's a problem is that the errors happen in ways that we can't eliminate altogether. However much Monster Cable would hope to convince you otherwise, and charge you a lot of money for the privilege. The bottom line is that our simple mathematical model is not taking into account all the physical phenomena. So our theory is imperfect. And in fact, if you want to think of it this way, reality is imperfect. Now that's sort of unfair to reality. I mean, it's sort of like, hey, I was here first. And you can sort of say to yourself, well, okay, so reality is imperfect. That means I have to, instead of coming up with I need to understand the imperfections, the things that were sort of messing up my simple model and incorporate them somehow. The bottom line is that our system architecture stinks because we did not allow for any sort of errors to happen. We didn't have a way of saying, oh, that was an error. Let's correct it now before it gets too far downstream and we lose track of what's error and what's signal. Okay, so the key to system design is to build something that if I have a bunch of building blocks and I wire them together according to the rules, the system will behave as I expect, okay, even though the real world is trying hard to sort of mess us up at some low level. So what we're going to do is we're going to develop a set of specifications that lets us look at the real world in a more abstract way, in a way that might be sort of impervious to sort of noise and things like that that's being introduced. So that's, we're going to spend the rest of our time and lecture here doing the engineering, figuring out what that specification should be in order for us to get where we want to go, which is being able to build a video processing pipeline that produces beautiful pictures at home, even though they were shot, Sunday afternoon at 6 o'clock in New Orleans, right? I want to be able to count, the number of hairs on the quarterback's nose without, I don't want completely accurately. Okay, so we want to produce specifications that are simple. In other words, we want to make sure that, I could, try to come up with this infinitely complicated model, and you say, well, how does this work? And you say, well, here's the 27-volume set that describes precisely, starting with quantum electrodynamics, how the 12-cent resistor that you just bought works. And you're sort of going, I don't think I'll be able to use that. Thanks. I'll look for a different component. So I want a simple model, and I want them to be, once I have that specification, I need to be able to build things that meet the specification. So we're going to come up with a digital specification. Okay, this notion of moving from the analog world to the digital world, the so-called digital abstraction, what we're going to do is to look at a particular analog phenomenon, in this case voltages, and interpret them digitally, right? And you can sort of say, well, why only 1 bit? You know, couldn't we get away with, say, 10 bits? You know, can we measure voltage? If I have a voltage between 0 and 1 volts, can I measure it accurately to the 1,000th of a volt? I mean, that doesn't seem too much to ask. Why am I only settling for 1 bit? Well, partly that's historical. Partly, making accurate measurements quickly was harder to do in the 30s and 40s as people started thinking about digital representations. But partly we'll see that it actually makes our systems wonderfully reliable, and that'll come out by the end of the lecture. So we're going to by going to this digital world where the phenomenon we're using will be interpreted either as a 0 or a 1, we'll get a lot of good things for that, good engineering things. Keep in mind, it's sort of tempting to sort of forget that this is still the real world. It still has all the problems of manufacturing variations and temperature-induced noise effects and things like that. Those are happening. So a digital system has all the same bad things happening to it as our picture processing pipeline. It's just that its specification, how we interpret the phenomenon that's actually happening, allows us to eliminate a lot of the errors. And then we use things like error correction to eliminate the errors that our low-level specification couldn't eliminate.